light comes on, so you can just put this part in your pocket. And then, well, you've been here since last week, so you know how I bother people to
Yeah.
repeat the questions.
Please remind me if I forget. Yeah.
And yeah, I've been telling people just to try to use the boards that move and not the boards that don't move, because the back can't see the bottom very well. So you
I see.
lift it about this high, maybe to right, just so the back row can see.
I see. Okay.
When we made this room, it used to be a library, and we changed it around. There are all these support structures up there, so we couldn't make it at a big angle. There's an engineering problem, so the room is a little bit flat, so that the back can't see as well as it should. Oh yeah. Anyway, are you ready to go? I can introduce you.
I think
Yeah?
so. Yeah.
All right, let's get started. So now we're happy to have Max Metlitski, who's been here since first week. He's going to give his lectures on, anomalies and topological quantum field theory from a condensed matter perspective.
All right. Thanks for the introduction. It was really fun to be here last week. Okay. So topological phases already got some coverage from Greg last week, and you'll hear from Tachikawa-san next week about anomalies. So I'll try to also give you a perspective on both subjects, but maybe somewhat more from condensed matter viewpoint. Okay, so one of the goals of condensed matter is to classify, characterize, and realize in the lab states of matter, new states of matter, and transitions between them. And we have, in the lab actually, experimentalists have lots of phases, and we are trying to understand them. And if you've ever looked at some data from, say, quantum Hall experiments, you see that we actually have lots and lots of phases. So it's yeah. it's a non-zero set. Okay, so there's existence. So these lectures, I'll be mostly focusing on gapped phases of matter. So let me define what I mean. Okay, so first of all, what's the setup? We are going to be working with systems on a lattice. Doesn't really matter what the lattice is, such that the Hilbert space is a tensor product of the sides of the lattice. If you are working, we'll distinguish systems of bosons and systems of fermions. In systems of fermions, there is a graded structure on this tensor product, not super important. Okay, and then there is a Hamiltonian H on this Hilbert space, which is local, so it's a sum over, let's call it Hi, where I is a side of the lattice, and each Hi acts on only some finite number of neighbors of side I. All right, and this lattice has some size. Let's call it L. And then we look at the spectrum of the Hamiltonian H. And it typically looks something like this. We work in a finite size L, so it's discrete. We assume the the Hilbert spaces are also all finite, just for simplicity. And I'll say that the Hamiltonian is gapped if there is a gap in the spectrum. Okay, delta, such that when I take the system size to infinity, delta is non-zero. Okay, gapped. So notice here I had potentially several levels below the gap, and the understanding is that there is perhaps a finite number of states below the gap, and they all become degenerate degenerate as L goes to infinity, and in this situation I'll also say that the Hamiltonian is gapped. As long as this degeneracy is stable, that is, it's not split by perturbations, and as long as it's sub-extensive, so smaller than exponential of the volume of the system. Okay, so these are the rules of the game. Now, so this is for one Hamiltonian H. I'll now define a gap phase in the following way. I'll define it as an equivalence.
It's down right, the next word.
Oh, perfect. Gapped phase. Gapped phase is equivalence relation on Hamiltonians on H's, such that two gapped Hamiltonians belong to the same phase if there is some path connecting them along which the gap doesn't close. So here I'm plotting the gap as a function of some parameter g. If there is some path between g1 and g2 such that delta remains finite, then we say that those Hamiltonians belong to the same gap phase. Okay, so these are the definitions. Now, so this would be two different phases. So this is phase 1, and well, potentially phase 2. So here the gap closes at some value of g, goes to 0, and this is a phase transition. Now it might be that there is some other path, maybe going out of the plane, along which the gap doesn't close, and then this would be actually the same phase. But if such a path doesn't exist, then we say that these are two different phases. Other questions? Okay, so now why do we study gap phases? So first, they're simpler, but they're actually still very non-trivial and rich. So we can make some progress and at the same time learn something non-trivial. Second reason is they exist in experiments. So quantum Hall states are an example. Topological insulators, superconductors, topological superconductors are an example. We'll actually mention some systems maybe. Quantum spin liquids, that is, quantum magnets with non-trivial, realizing non-trivial gap phases. People have been searching for those for many years. There are some candidates. People are not sure. Okay, so that's kind of experimental reason. Another reason is that many of these gap phases at low energies flow to topological quantum field theories. So maybe you can learn something about topology by studying them. Actually, I'll only be interested in gap phases that do flow at low energies to topological quantum field theories. And the last reason is that actually we can learn something about gapless phases by studying gap phases. And the way we do that is that some gap phases have gapless boundaries. And we can get information about those gapless boundaries and constraints on the dynamics of those gapless boundaries by studying the bulk. And that's really the perspective of anomalies. So we'll talk about this quite a bit. Okay, so let's see what kind of gap phases we can have. Gapped phases. I'd like to divide this into two broad categories. One category I'll call intrinsic topological order. intrinsic topological order. And another category I'll call invertible. So here are some, let's start with this category, with phases with intrinsic topological order. So the main property of these phases, okay, I don't know which one is the main, they're like heads and tails of a coin, but they have a robust ground state degeneracy on a non-trivial spatial manifold. Robust ground state degeneracy on a non-trivial manifold. Now, for a condensed matter theorist, a non-trivial manifold typically means a torus, because it's really hard to, to put, well, even for a theorist, right? If you have a lattice, how do you put it on a sphere or a donut with two holes? Or, but eventually, when we take the continuum limit and write down some topological field theory, we might be even able to study, somehow study the system on a manifold more non-trivial than a torus. But a lot of the time, even on a torus, we see that there is a finite ground state degeneracy like this that remains stable, that remains unsplit as we change the couplings. Okay. So the other property is that they have excitations that cannot be created by local operators from vacuum, from the ground state. So let's say here is my, let's say we are in two spatial dimensions. So this is 2 plus 1D. So here is the spatial slice, and we might have some we might have some eigenstates. It kind of look like there are some excitations, one sitting here and one sitting here. But it might be the case that there are no two local operators localized near the positions of these excitations that would create this state out of the vacuum. And we will discuss models like this. Okay, so what are some examples of this intrinsic topological order? So first of all, in 1 plus 1 dimensions, there are none. They don't exist. In 2 plus 1 dimensions, however, they are very rich. 2 plus 1D. These are so-called anion models. The Chern-Simons theory that Greg talked about last week is an example of a low energy, well, of a topological field theory that describes these anion models at low energies. More generally, they are described by what's known as unitary braided modular tensor categories. So it's some mathematical structure that's on one hand has been extensively studied. On the other hand, there are still interesting surprises. We will not use this full machinery. We'll have only very, very simple examples of this that we'll discuss. This structure is for phases of bosons. I don't think it's completely understood what the corresponding structure is for phases of fermions. At least not all the details are ironed out. Okay, so this is in 2 plus 1 dimensions. What about 3 plus 1 dimensions? Well, we don't. The subject is not as well established, but first of all, gapped phases with intrinsic topological order in 3 plus 1D exist. And the belief is that they're all more or less digraph-Witten theories for a finite gauge group G, with some, not quite that, but with some, but almost. Digraph, I have digraph spelled somewhere, but let me just write DW. DW theories for a finite gauge group G. Okay, this is at least an example, and we will actually discuss this example in a lot of details. We'll spend a lot of time defining these digraph-Witten theories. So this is for bosons. Okay, again, fermions are more complicated. And okay, so this is 2 plus 1D, 3 plus 1D. This is more or less the only dimensions that, as a condensed matter theorist, I'm interested in. But in high dimensions, I think the subject is largely largely unexplored. So lots of room. Another comment that I would like to make, now that we started talking about 3 plus 1 dimensions, is that there are gap phases in 3 plus 1 dimensions that cannot be described by ordinary topological field theories at low energies. Here is an example which is kind of, maybe seems like a dumb example, but not all gapped phases are described by topological field theory. Well, for topological field theory, we need a lot of things, right? You expect that kind of at the very least you should get low energies. You should get kind of a Lorentz invariant, so space and time should be the same, at least when you go to Euclidean signature. Well, we are starting with some lattice model, so some direction might be special in space, let alone time. So it's kind of miraculous even if you just get rotational invariants emerging at low energies. But here's an example of a phase where clearly rotational invariance does not emerge at low energy. So let's just take a stack of two-dimensional phases with intrinsic topological order. Stack along some z direction, so let's call this z. If you wish, this can be like one of the theories that Greg discussed last week. Say it's U1 Chern-Simons theory at level 2. I'm afraid all my levels will be doubled compared to Greg's levels, but anyway, this is the theory where the ground state on a torus is twofold degenerate, right? So if I stack these planes with periodic boundary conditions along some z direction, each layer has a degeneracy of 2 on a torus. If I have L of these, then the degeneracy goes as 2 to the L, right? So I don't have a finite degeneracy. I have a degeneracy that grows exponentially with the length of the system, but it's still smaller than exponential of the volume of the system. Okay, that's kind of strange, but let's keep going. Well, clearly one direction is special, right? That doesn't happen if I just make the x and y directions bigger. Also, if I take some anion, so this U1 level 2, as Greg discussed last week, it has Wilson lines, right? So these Wilson lines end on particles, and this the Wilson lines are particles. So if I take a particle, take an anion from one of these planes, it can move in the plane, but it cannot move out of the plane. So clearly, this is very anisotropic. So it's not described by a topological field theory of the usual kind. You might say, okay, this is just some very dumb example. Let's just rule it out. But turns out that there are examples which are not obviously stacks of two-dimensional planes, and in fact are categorically not stacks of two-dimensional planes, but which nevertheless have some of these features that they're not described by an ordinary topological field theories at low energies. And such phases are known as fracton phases. As far as we know, they start in 3+1 dimensions. We don't know analogs in 2+1 dimensions. And they're a very active subject of research. They're not as dumb. They're not as dumb as this. They're actually really cool. For instance, the degeneracy on some 3 torus can go not as 2 to the L, but can jump around depending on whether L is a power of 2 and which power of 2 it is. So there are some very interesting physics going on, but for the purpose of my lectures, we'll forget about these fracton phases. We'll only talk about gap phases that can be described by topological field theory at low energies.
Why do you say that non-trivial topological order does not exist in 1+1 dimension?
Well, I want a stable. The question was, why did I say that non-trivial? Why did I say that non-trivial topological order does not exist in 1+1 dimensions? So mathematicians would tell you that there are topological field theories in 1+1 dimensions. Now, for my purposes, I want gapped phases which are stable. So I want if there is a degeneracy, where was my degeneracy? If there is a degenerate manifold, if there is a degenerate ground state manifold, I want that degeneracy to be stable to small perturbations. I don't want a situation where as I change some parameters, these states split. And in 1+1 dimensions, as far as we understand, the topological field theories that mathematicians write down actually don't have this property. There, if you turn on small perturbation, the degeneracy splits.
When you say perturbation, you mean literally all possible finite range interactions Hamiltonian that you can turn on?
Yes. Yes.
Could you repeat that?
The question was, when I say perturbation, do I mean all possible small, I'm going to add the word small, perturbations, local perturbations to the Hamiltonian? And my answer is yes. So right now I am not, when I'm having this discussion of gap phases, right now I'm ignoring any symmetry. So with no symmetry. Let me put. No. Yes, Tom?
So you're not going to talk. What about things like polyacetylene? Where I thought those were topological. You have, you have solitons and things stuck to them.
Yeah. So those maybe you can think of those as kind of translational symmetry breaking. Yeah. The question was whether I was going to talk about.
Where does that fit in? I thought that those were topological bases.
So we will talk about. So first, let me repeat. Question was, where does polyacetylene fit in? And Tom is saying that he thought those were topological phases. So those, first of all, maybe more precisely characterized as, at least initial discussion is more like topological defects, and it's about systems with symmetry that's spontaneously broken, and what can happen on the defects of the symmetry, say domain walls of vortices, and we will talk about symmetry shortly. Yeah, but right now I'm not imposing any symmetry. Yes.
Is there any topology? Is there any gap phases which has emergent and Lorentz invariance and not described by TQFT?
The question was whether there are any gap phases that have emergent Lorentz invariance but are not described by topological field theory of some kind. I'm not aware of such. Is anyone in the audience aware of such? But there are essentially no proofs. Actually, in 1 plus 1 dimensions, there are proofs. One can prove that there is no intrinsic topological order in 1 plus 1 dimension with the definition that I've given. Other questions? Romer?
Are these fractal models sufficiently local, or they're having non-local?
They're local. So everything I say will be for local Hamiltonians. Local interactions. Yes, actually they're finite range interactions. Yeah, they only discovered I think in 2012 maybe. Is it right? Or 2013? Is that? Oh, 2005. I see. But I think many of us remained unaware until quite recently. Other questions? Okay, so let's. So we'll only talk about gap phases that are described by topological field theory. Condensed matter physicists sometimes refer to those gap phases as liquids. So if you hear liquid, that's more or less what it means. Okay, so far I've described the properties of these phases with intrinsic topological order. What about this other category that I defined, invertible phases? So these invertible phases are actually much better understood than these phases with intrinsic topological order, to the point where many people believe that there is a complete classification of them. But first, let me define what I mean by an invertible phase. So first of all, why the name invertible? Well, the reason is that these invertible gap phases actually form an abelian group. Form an abelian group. What is the addition in the group? So suppose we have two phases, one with a Hamiltonian H1, another with Hamiltonian H2. Then the addition is simply stacking the two systems, right? Non-interacting stack, where whatever in the top layer I have Hamiltonian H1, in the bottom layer I have Hamiltonian H2, and there is no interaction between the layers. I'm using layer as metaphorical, that this can be of any dimension. Okay, so this is addition. What is 0 in the group? By the way, it's clear that this this addition is abelian, right? Because it doesn't matter if I change the order. Clearly, it's the same phase. What is the 0? Zero is what we call the trivial phase, and the trivial phase is the one whose ground state. Well, remember these phases are equivalence relations on Hamiltonians, and the trivial phase is one where I can deform a Hamiltonian such that the ground state is unique and is just a product. It's just a local tensor product. Right. So on each, here's my lattice, and the ground state wave function is just a, is just a tensor product over each side, completely unentangled. Okay, so this is the zero. So what is the inverse? Well, the inverse is for a phase 0 inverse. For a phase A, I define the inverse to be phase B such that when I stack them together and then I stack them together, right? I use my addition, and I start tuning parameters in the Hamiltonian, potentially coupling top layer and bottom layer, such that at the end of the day I get my zero phase. That is, I get a Hamiltonian whose ground state is unique and is just this complete tensor product state.
When you speak of different phases of the system, are you fixing the lattice or not?
So there is some stabilization that needs to be done, right? So I should be able to throw in extra degrees of freedom. So I don't want to discuss in detail how to do that stabilization, but yeah, so in principle because I'm not imposing any symmetry of the lattice here, right? I'm currently discussing with no symmetries, so I'm not really fixing the lattice. By the way, the question was whether I'm fixing the lattice. Yes?
Is the statement that when you combine them and stack them, that it stays in the same phase when you introduce couplings between the lattices?
So to have so first of all,
Also, could you repeat the question?
Can you repeat the question and then I can
Is the statement that when you do the abelian group action, that it stays in the same phase when you introduce now a coupling to do the sort of inverse trick, you would need to do something like this, right?
So the question is whether when I stack and so first of all, the question is whether when I stack it remains in the same phase, right? So I add.
And you talked about couplings. You talked about changing the couplings.
So I add A. I do A. This is in phase A. This is in phase B. So I'm defining a phase A plus B as an equivalence class of Hamiltonians that can be obtained from this Hamiltonian acting on these two layers by deforming the couplings, keeping the gap finite. Now, when I say that there is an inverse, I mean that I can deform the coupling until the system is in this ground state, which is completely decoupled. Other questions? Okay. So this is what I'll mean by inverse. Now clearly, not all phases have inverses. So let's write that down. Not all phases have inverses. In fact, any of these phases with intrinsic topological order, the way I've defined them, don't have inverses. Here's the reason why. Let me think about one of these phases with intrinsic topological order on a non-trivial manifold, say on a torus, e.g. if we have non-trivial, if we have intrinsic topological order, no inverse. Right, so let me start with a phase with a non-trivial intrinsic topological order on the torus, right? So there is a ground state has some degeneracy, which is stable against small perturbations, we said. So this is for phase A. Now I try to introduce some phase B to kind of to get to stack and to get 0. Maybe I add a Hamiltonian for B that also maybe has ground state degeneracy, maybe doesn't have ground state degeneracy. But so when I just stack things, the ground state degeneracy is going to be a product. Let me call the ground state degeneracy G. And since I was saying that this must be stable, right, and this is a stable degeneracy, so I have this very, I have something with finite ground state degeneracy, and now I'm asking that as I deform parameters, I should, should deform to something where there is a unique ground state. Let's say there are 2 here, 2 here, so there are 4 here. I want to deform to something where there is only single ground state which is completely unentangled, like I had there. So clearly I cannot do this without the gap coming down. Yes?
Does this mean that these invertible theories always have a unique grounds?
Yes. The question was whether this means that invertible theories have a unique ground state, and the answer is yes. That's a very good point. Invertible phases have a unique ground state on any spatial manifold. Moreover, if we calculate the partition function on some space-time manifold M, this is pure phase up to local counter terms of the type that Jaume discussed. And we'll talk a lot about, actually saying what this phase is, how it depends on the manifold, and so on. Well, of course, as I said before, we have trouble putting our system on an arbitrary spatial manifold, let alone on any space-time manifold. So what we have in mind is that we go from our lattice Hamiltonian to a topological field theory description, and then we compute the partition function of that topological field theory on a general space-time manifold. Okay. So just to complete this definition, invertible phases are those that have an inverse, and then by construction they form a group, an abelian group. Okay, abelian groups are kind of nice. That's why there is some hope of classifying them, of classifying these phases. That is, not a billion groups. A billion groups are classified. Okay, but what is interesting about this invertible phases? It looks like they are very, very boring. They have a unique ground state on any manifold. The partition function is a phase. No non-local excitations. All excitations must be local. All excitations are local, can be created by local operators from the ground state. So what's interesting about them from an experimentalist standpoint? An experimentalist cannot measure, partition function on RP3. So what's interesting about them is that they have protected edge modes. So here, I'm thinking about taking my system on a spatial manifold, I don't know why, that has a boundary. So even though, when the manifold Y is closed, when it doesn't have a boundary, even though there is this ground state which is unique and gapped, on a manifold with a boundary, there is something interesting going on the boundary, and on a manifold with a boundary, in fact, these phases cannot have a unique gapped ground state. So interesting dynamics on the edge. Edge states are anomalous. And by anomalous, I mean that they cannot be recreated without the bulk. But in the field theory sense, it turns out that they will have Toft anomalies, gravitational Toft anomalies. Now, you can imagine that for a given bulk Hamiltonian, I can have many boundary Hamiltonians. I can go ahead and I can do anything I like to the boundary Hamiltonian. And I can ask, well, what happens? So in general, we can get phase transitions on the boundary without phase transitions in the bulk. Right? I just change couplings on the boundary without doing anything in the bulk. So one bulk phase, many boundary phases. Now, as I said, the boundary cannot exist without the bulk, and the boundary the anomaly of the boundary is determined by the bulk. So then clearly, because I'm only changing the boundary without changing the bulk, clearly the anomaly cannot renormalize because the anomaly is determined by the bulk. So this is a very nice way to understand the non-renormalization of Toft anomalies in quantum field theory.
Is this the same thing as the anomaly in flow in the high energy community? Is this the same thing that you're describing?
It is, yes. And we will see very concrete examples shortly.
Could you repeat the question?
The question was whether this is the same effect as anomaly inflow that people in the quantum field theory community are familiar with. It is, although maybe slightly more general, but basically yes. Any other questions? Yes?
So if we have a unique ground state which is completely gapped, can we safely say the system is in the invertible phase?
Yes.
Could you repeat that?
The question was whether if you have a unique ground state on any spatial manifold that's gapped, whether we can say that the system is in an invertible phase, and the belief is yes. Other questions? All right, so let's have an example. Let's see how we're doing for time. Okay, let's discuss an example of an invertible phase, and this will involve fermions in 1+1 dimensions. Called Majorana wire in 1+1D. This is due to Kitaev. So before I go on with this example, kind of major purpose of my lectures will be to explore these invertible topological phases and the anomalies of the boundary and the correspondence between the two. But let's proceed with this example. So this is a system of fermions in 1+1 dimensions. So here is the Hilbert space that we'll discuss. Imagine that we have a chain, right? So it's one spatial dimension, chain of fermions, labeled with sites labeled by I, running from 1 to n. And I have a fermion sitting on each side, right? So I have fermion operators satisfying the standard algebra. So on each side, right, I can have Ci dagger Ci equal to 0 or 1. So the fermion is either empty or occupied on site I. Okay. Now for this complex fermions, I can rewrite in terms of Majorana operators. I can write Ci equal to 1/2 gamma I plus I gamma I bar. Don't confuse square root of -1 and index I, where these gammas and gamma bars are Hermitian. And they satisfy the following anti-commutation relations. That is, they square to 1, and the ones sitting on different sides do not commute. Right? So different Majoranas anti-commute. Gamma I bar, gamma j bar is equal to 2 delta ij, and gammas and gamma bars anti-commute. Okay, So I can rewrite things in this way, and then my condition that, well, my Hilbert space, which is that every site I can be occupied or not by a fermion, it's equivalent to, if I rewrite Ci dagger Ci as 1/2 1 plus, this becomes 1/2 1 plus I gamma I bar. So I gamma I bar can be plus or minus 1, with plus 1 corresponding to occupied and minus 1 corresponding to empty. Yes? All right. So let me write a Hamiltonian on this Hilbert space that will represent the trivial phase first, and then I'll modify it slightly to get a Hamiltonian that is in a non-trivial invertible phase. So consider first H naught, which is sum n. By the way, it's nice to draw a picture here where each complex fermion C I split into these two Majoranas gamma and gamma bar, so I'll draw pictures like this. So this is gamma 1 bar, gamma 2 bar, gamma 3 bar, and then dot dot dot. Here is gamma n bar, I gamma bar. Okay, so let me first start with a Hamiltonian just like this, where I simply couple the gammas and gamma bars on each side. Right, so this is nothing but remembering our relation between gamma bar and C dagger C. So the ground state of this is going to have all the, we want to minimize the energy, so we want C dagger C equals 0 on each side. That is, we want I gamma I bar equal minus 1 for all sides. So that means that the fermion mode on each side is empty, right? So it's empty, no electrons. So this ground state is exactly a product state that I've described here. It's really just trivial, unentangled state. Okay, so ground state is product state. If I want an excitation, right, I can flip one of these gamma bars. That costs me energy 2. Delta equal to 2. So there is a unique ground state and it's gapped. And excitations can be created by local operators, right? If I want to switch the sign of gamma bar, I just act with one of the gammas, right? It anticommutes, so it I gamma j, right? So to create one of these excitations, as I flip the sign of gamma bar on some side, can be created from ground state, by gamma j, say, on ground state. So it satisfies, okay, trivial state satisfies all the properties of an invertible phase. It's the zero state, the zero phase. Not very interesting. Let's modify this slightly to get a Hamiltonian in a non-trivial phase. Trivial phase. Now consider H1, which is the following. Gamma I bar, gamma I plus 1. Right, so I take each gamma bar and couple it to the gamma on the next side. So the picture now looks like this. Gamma 1 bar, gamma 2 bar, 3 bar, gamma n bar, and I couple things in the following way. Okay, and let's say for now I'm on a circle, on a ring. Let me use periodic boundary conditions. So then, this one is coupled to this one. I don't know if I can pull this off, but all right. So, okay. Now, in terms of the algebras of these gammas and gamma bars, there's not a whole lot of difference, right? Each of now it's kind of like I regroup my Majoranas into complex fermions made out of combinations of gamma I bar and gamma I plus 1, and each one of those complex fermions can be filled or empty. So it's the same spectrum: I gamma I bar gamma I plus 1. Can take on values plus or minus 1. Ground state is unique, is when all of them are minus 1. Ground state minus 1, unique. Gap delta equal to 2. Right, so this okay, so let's see if this is a different phase from what we were discussing before. Yes.
Can you remind us what H1 looks like in terms of C's?
Good. So I can rewrite gammas in terms of C's and C daggers, and this will be something. I won't work out all the factors of 2, but this will be something like I equal 1 to n. Ci dagger Ci plus 1 plus Ci plus 1 plus Hermitian conjugate, more or less. You can do the exercise. So, right, so it has electrons hopping between nearest neighbor sites, and it has some C term, which is like a superconducting hopping. I don't know. Corresponds to basically p wave. If you want to think in terms of a superconductor, this is p-wave pairing of fermions. Other questions? The question, by the way, was how does the Hamiltonian look in terms of C's and C daggers? All right, so there is a unique ground state on a circle, same as for H0. But what's different is that if you consider this Hamiltonian on an open segment, then the ground state is not unique, right? On an open interval, can I do something illegal and erase this? In the interest of time, let me just do that. Right. So now let me consider actually a much more physical situation. From an experimentalist viewpoint, let me just consider a open chain like this. So I now see probably needs to be n minus 1. So now I have these dangling Majoranas at the ends, gamma 1 and gamma n bar. And now the ground status of this open chain is twofold degenerate. Ground state is twofold degenerate because if I group these two Majoranas into a complex fermion, it can be empty or occupied. I can have gamma 1 gamma n bar equal to plus or minus 1. Okay, so for an open chain, it's gapless. Ground state is doubly degenerate. Moreover, if I think about this boundary, if I kind of forget about the rest of the chain, right? If I just look at one boundary, it's anomalous. I cannot have a single Majorana in 0 dimensions, right? Because what would be the Hilbert space dimension? Here I have two Majoranas, gamma 1 and gamma n bar. Hilbert space dimension is 2. So each one is like square root of 2. But what is Hilbert space of dimension? Square root of 2. So edge is anomalous, cannot exist in 0 plus 1D. Because then the dimension of the edge would be square root of 2. Now, this is not a fluke. Turns out that this degeneracy of the ground state for an open chain is stable to perturbations. How do we see that? Well, first of all, the most naive thing that you would write down that would split this degeneracy would be to write down delta H equal lambda I gamma 1 gamma n bar, right? It would give different energy to these two states. But this is a non-local perturbation, right? I'm now considering this open chain, so site 1 is very far from site n. So this is the non-local coupling, prohibited. Non-local. But there is we can also think about it in the following way. So these two states, two degenerate states, actually have different fermion parity. Let's quickly see that. Let me consider two ground states have opposite minus 1 to the f. let's consider -1 to the f, the fermion parity. Okay. It's really a product of fermion parity on each side. But now I can rearrange this product in the following way. Gamma n bar. I move this gamma n bar over to here, and the rest is like this. But my bulk Hamiltonian imposes that these factors are all 1, right? So acting on either of the two degenerate ground states, this gives me 1. So on the two degenerate ground states, this reduces to minus I gamma 1 gamma n bar. So I see that my two ground states have opposite fermion parity. Okay, so what? So let 0 be the ground state with even fermion parity. Then I can get the state with odd fermion parity. By acting on state with even fermion parity with either gamma 1 or gamma n bar 0 plus. So gamma 1, of course, is odd under fermion parity, and so is gamma n bar. Okay. You can say, so what? This is just some model. Maybe if I perturb it, these two states with opposite fermion parity split. That turns out not to happen. And in fact, if you perturb Okay, so first of all, there was this gap delta that was initially equal to 2, and the gap cannot close immediately. What could have happened is that as you perturb these two ground states on an open chain, it could happen that they split. Turns out that the splitting is exponentially small in the system size. Well, I called this n. So. The reason is the following. So as you perturb, you can actually show that the action of -1 to the f on the low-lying states takes a form very similar to the form it took here, right? Where gamma left and gamma right are two operators that are localized near the left and right ends of the chain, and kind of exponentially localized over some finite length c. That's finite in the limit when n goes to infinity, and they anti-commute with fermion parity. And same property, square to 1 etc., etc. And from this factorization of Fermat parity, one can actually show that these states cannot split more than by an exponentially small amount. How are we doing for time?
6 minutes.
6 minutes. So let's maybe
5 minutes.
let's maybe quickly show this, that this factorization implies that I cannot have a splitting. So really, so first of all, this equation should be understood as the action of -1 to the f on the low-lying states associated with the boundary. Statement number 1. Second statement is that if this is true, then both gamma left and gamma right commute with the Hamiltonian, whatever the new Hamiltonian is, the perturbed Hamiltonian, up to terms exponentially small in the system size. Okay, it's a nice argument. Kind of makes sense, right? If H is local and then gamma factorizes into something acting on the left and right sides, then better the left and right sides individually commute with H. So how do we see this from the top line? Let's consider a matrix element A gamma L H gamma L. By the way, these gammas are Hermitian, although that's not too important. You can choose them to be Hermitian. Let's consider this matrix element. Okay, H, whatever the perturbed Hamiltonian, is still local. And A and B here are two states in the low-lying subspace. We don't know yet if they split or not. They are trying to show that they cannot split. Right? Okay, so H is a sum of local terms. Now, if I is far from the left end, then because gamma L is localized near left end, it must commute. If I far from left end, gamma L HI equals 0, and then we have that this is equal to A HB. Okay. Now what if I is not far from the left end? If I is near left end, well, then it must be far from the right end because we are taking a long chain. So then let me call this, well, then A gamma left H gamma left B. So gamma is odd under Fermat parity, H is even, gamma is odd, so I can put in factors of -1 to the f here. Okay, but I know that -1 to the f the assumption is that it acts in that factorized way on the left and right ends. So I can put in here gamma right, gamma left, H, gamma left. I think this should be, if I take Hermitian conjugates correctly, should be like this. But gamma left squared is 1, so this is A, gamma right, H, gamma right, B. We assumed, it's not H, H, I. We assumed I is far from the right end because it's near the left end, so this gamma right commutes with HI, so this is just A, HI, B. So this matrix element of H between the states transformed by gamma left is the same as non-transformed. So that means that top line implies this. And because gamma left anti-commutes with Fermat parity, this implies that the ground state is twofold degenerate, the degeneracy cannot split. So really all the hard work is to show this fact, that on the low-lying states, as you perturb the Hamiltonian, the Fermat parity still looks like it looked in the non-interacting case, in this exactly solvable case, except that the gamma 1s and gamma n's get kind of fattened up, and essentially all the hard work for these kinds of arguments was done by Matt Hastings in 2004. So one can just use that technology. So I guess I'm out of time. All right. So next time we will see that. Okay. So first of all, because it's clear that this is now a phase which is distinct from the trivial phase defined by H naught, we will see that it's actually a Z2 phase in the sense of this abelian group of invertible phases that we discussed earlier. And we'll also discuss how to detect it on a closed chain without looking at the boundaries. And we will discuss how to write down its partition function in an arbitrary spin manifold. Okay, let's stop here.
Well, if not, we can be done for the day. We'll see you all tomorrow morning at 9. Let's thank Max again.
Yeah, sure. Let's go.